and welcome everyone to a new video in our unit on linear algebra. Eigenvectors and eigenvalues are arguably the most useful concepts in all of linear algebra. They show up in some form or another in almost all areas of physics and data science. They're used everywhere from finding the optimal flow of nutrients through a slime mold network, to finding the atomic orbitals for a hydrogen atom, to the Google PageRank algorithm. In this video, we'll discuss the meaning of eigenvalues and eigenvectors, as well as singular values. Then we'll explore some algorithms to calculate them. When someone hands you a matrix, they aren't just handing you an array of numbers, they're handing you a basis and scaling factors. If A is a linear transformation acting on some vector space V, then the non-zero vector V is an eigenvector of A if A acting on V produces a new vector that is a scalar multiple of V. The scale factor is called an eigenvalue. For example, this shows a linear transformation by the matrix 7, 4, 4, 10. The red lines are the two directions that remain unchanged throughout the transformation. Those directions are its eigenvectors. The eigenvalues are the percent that a point has shifted along each eigenvector compared with the beginning of the transformation. We can implement this for an n by n matrix A by looking for solutions to A minus lambda times the identity acting on V equals 0 for some non-zero vector V. This only happens when A is singular, that is, it has rank less than n. If a matrix is singular, it has zero determinant. So the determinant of A minus lambda times the identity is also equal to 0. An eigenvalue, lambda, is a solution to the characteristic equation P is equal to the determinant of A minus lambda times the identity is equal to 0. This means that the eigenvalues are complex numbers lambda 1 through lambda n that are the roots of the characteristic polynomial P, which is equal to minus 1 to the n lambda minus lambda 1 times lambda minus lambda 2, and so on and so forth through lambda minus lambda n. Every n by n matrix has at least one, and at most n distinct eigenvalues. The algebraic multiplicity of an eigenvalue lambda I is the power k of the term lambda minus lambda I to the k that appears in the factorized polynomial. You can calculate the eigenvector vi associated with the eigenvalue lambda I by solving the equation A minus lambda I times the identity acting on vi is equal to 0 by Gaussian elimination or another standard method. Sometimes there are more than one linearly independent vector that solves A minus lambda I times the identity acting on vi equals 0 for a given lambda I. The set of vectors E that satisfies this equation is called an eigenspace of lambda I. The number of linearly independent non-zero vectors in E is called the geometric multiplicity of lambda I. Given k distinct eigenvalues lambda 1 through lambda k, then the corresponding eigenvectors v1 through vk are linearly independent. This means they span a k-dimensional Euclidean space. If a real n by n matrix A has n distinct real eigenvalues, then their corresponding eigenvectors form a basis for Rn. If the matrix A has n distinct complex eigenvalues, its eigenvectors v1 through vn form a basis that spans Cn. A matrix is called complete if and only if its eigenvectors span Cn. Now that we've covered a few basic facts about eigenvalues and eigenvectors, let's discuss two ways of decomposing matrices that reveal some properties about them. First off, we'll look at diagonalization. An n by n matrix A is called diagonalizable if there exists an invertible matrix S and a diagonal matrix D such that S inverse AS equals D. You can rewrite this by multiplying by S on the left so that AS equals SD. Now let's look at the kth row of this equation. A acting on sk equals dk times sk. This is the eigenvector equation for A, where sk is the kth eigenvector and dk is the corresponding eigenvalue. Geometrically, the process of diagonalization acts as a transformation that rotates and stretches the x and y axes to align them with the eigenvectors of A. For example, let's diagonalize the matrix 1, 1, 6, 0. The characteristic polynomial lambda squared minus lambda minus 6 has two roots. Lambda 1 equals 3 and lambda 2 equals minus 2. The eigenvectors are given by 1, 2 and minus 1, 3, respectively. S, then, is a matrix made from the eigenvectors, and D has the corresponding eigenvalues along its diagonal. We can invert S using any technique we'd like, which gives us S inverse equals 1/5 times the matrix 3, 1 minus 2, 1. The matrix S now acts as a linear transformation that converts the vector 1, 0 into the first eigenvector 1, 2, and the vector 0, 1 into the second eigenvector -1, 3. Symmetric matrices have some additional nice properties of their eigenvectors and eigenvalues. For an n by n symmetric matrix A, the eigenvalues of A are real. The eigenvectors corresponding to distinct eigenvalues are orthogonal. If A has n distinct eigenvectors, then they can be used to form an orthonormal basis for Rn. The spectral theorem states that A admits a decomposition QD/Q inverse, which is equal to QD/Q transpose, where Q is an orthogonal matrix whose columns are given by the orthonormal eigenvectors of A, and the entries of D are its corresponding eigenvalues. For example, take the matrix 1, 2, 2, 4. Its characteristic polynomial, lambda squared minus 5 lambda, has roots 5 and 0, which correspond to the eigenvectors 1, 2, and minus 2, 1, respectively. Both eigenvectors have length root 5, so we can divide the whole S matrix by root 5 to get our Q matrix. 1 over the square root 5 times 1, 2, minus 2, 1, and Q inverse is equal to Q transpose. Now Q is a rotation about the origin that aligns the unit vectors x hat and y hat with the unit vectors v1 hat and v2 hat. The second decomposition we'll look at is the singular value decomposition, or SVD. The SVD is a generalization of the eigendecomposition of a square matrix to a general m by n matrix. What the SVD does geometrically is break up a linear transformation into a combination of unitary transformations and rescalings of mutually orthogonal directions. Before we can get into SVD, we must define singular values. Given an m by n matrix A, the singular values sigma 1 through sigma k are the positive square roots of the eigenvalues of the associated gram matrix K equals A transpose A. The singular value decomposition says that any m by n matrix A of rank R is greater than 0 can be decomposed into A equals U sigma Q transpose, where U and Q are unitary matrices and sigma is a diagonal matrix whose entries are the singular values of A. The matrix Q is an R by n matrix, where R is the rank of A, whose columns are given by vectors that form an orthonormal basis for the gram matrix K. Along with sigma, the QIs are ordered in decreasing order of singular value. We can construct the R by M matrix U from the equation AQ equals sigma U. We know that U is a unitary matrix, so the vectors vi, given by the product of a diagonal matrix with U, must be orthogonal. We can show this is true because the inner product of vi with vj equals qi transpose A qj. Since A transpose A is the gram matrix K and the Q's are its unit eigenvectors, then this is equal to sigma I squared times qi dot qj. Since qi and qj are orthogonal, then so are vi and vj. That tells us that the associated unit vectors ui equals vi divided by its norm, sigma I, equals A times qi divided by sigma I. If the rank of A is less than m, then additional unit vectors can be added so that U is an orthonormal basis for Rm. Let's look at an example of this. Here our matrix A is 3, 1, 1, 2, and this is the linear transformation made by A. Its associated gram matrix is 5 times the matrix 2, 1, 1, 1. The first eigenvalue for the gram matrix is 5/2 times 3 plus root 5, and it has corresponding eigenvector 1 plus root 5 over 2, 1, which can be normalized to 0.851, 0.526. The second eigenvalue is 5/2 times 3 minus root 5, and it has corresponding eigenvector 1 minus root 5 over 2, 1, which can be normalized to minus 0.526, 0.851. So our matrix Q is the matrix of unit vectors of the gram matrix, and the entries of D are the square root of its eigenvalues. We can use our formula UI equals A times QI divided by sigma I to find the columns of U. We get U equals 0.851 minus 0.526, 0.526, 0.851. We can see the effects of each of these matrices in constructing the linear transformation for A. First, Q transpose is a clockwise rotation. Then D scales the new x and y axes by the singular values sigma 1 and sigma 2, respectively. Then U is a counterclockwise rotation. Singular value decompositions are used frequently in signal analysis, image compression, and anywhere the eigenvalue analysis might be useful, and your matrix just isn't square. Lastly, we'll go over some numerical techniques for computing eigenvalues without having to numerically solve for the roots of a degree n polynomial. All of the algorithms we've used so far have been direct algorithms. That is, they take you from the original matrix to some other matrices exactly. Fast algorithms for computing eigenvalues, however, use iterative techniques. An iterative system starts with a vector u0 as the zeroth iteration and repeatedly applies some linear transformation m to it, such that the I plus 1th iteration is given by applying m to the ith iteration. So ui plus 1 equals m ui plus c. The goal of a system like this is to find a convergent solution such that un approaches some steady state u star as n goes to infinity. U star is the solution to the fixed point equation, U star equals m U star plus c. A fixed point solution is stable if and only if the spectral radius rho of m is less than or equal to 1, where the spectral radius is the maximum of the absolute value of all the eigenvalues of m. If A is complete, then the general solution to the iterative system ui plus 1 equals m ui is given by ui equals a1 lambda 1 to the I v1 plus a2 lambda 2 to the I v2, and so on and so forth through an lambda n to the I vn, where the vn's and lambda n's are the eigenvectors and eigenvalues of m. Using these facts about iterative systems, we'll look at the first method for calculating eigenvalues of a matrix. This algorithm is called the power method. This method takes advantage of the fact that we can write the ith iteration of a system ui equals m to the I u0 as a sum of terms aj lambda j to the I vj. We can always order the eigenvalues according to their absolute value, which tells us that lambda 1 to the I is much greater than lambda j to the I for large I. Then lambda 1 approximately equals ui sub j divided by ui minus 1 sub j, where ui sub j is the jth component of ui. Here's an example of this for the matrix 1, 2, 3, 2. For reference, it has dominant eigenvector 0.555, 0.832, and dominant eigenvalue equal to 4. For this algorithm, you start with a guess for your first eigenvector. Here, we picked 1, 0. The next step is applying a to it and then normalizing it to get the next eigenvector. Then we calculate the first lambda value as the first component of v1 divided by the first component of v0. You'll note that we're using the unit eigenvectors here. That way, the vector v will converge to a unit eigenvector rather than some very large multiple of the non-normalized eigenvector. Then we repeat this. Here are the first 7 steps of the iteration. You'll see that this quickly converges to the correct values for both the unit eigenvector and eigenvalue. Variations of this method can be used to iterate through and solve the whole eigensystem. However, that is computationally very costly and slow. The QR algorithm, on the other hand, is a deceptively simple and quickly converging algorithm for finding all eigenvalues for a given matrix in one go. To calculate the eigenvalues for A, let's set the 0th iteration to A. Then we do a QR factorization of A0, so that A0 equals Q0 R0. The next step in the iteration is multiplying those factors together, but in the opposite order. So A1 equals R0 Q0. Then repeat steps 1 and 2 so that ai plus 1 is the product of ri and qi, which in turn can be factored as qi plus 1, ri plus 1. Let's try this with the same matrix we had in the previous example. A equals 1, 2, 3, 2, and its eigenvalues are 4 and minus 1. I'm going to graphically illustrate each transformation as a linear transformation on a circle, taking it to a rotated ellipse. Each iteration brings the ellipse closer to having its semi-major axis along the x direction and semi-minor axis along the y direction. As I keep iterating, the matrix AI approaches an upper triangular matrix whose diagonal values are the eigenvalues of A. It turns out that the QR algorithm is a cleverly disguised implementation of the power method. See if you can convince yourself why that is. Thanks for watching, and I'll see you next time.